All right, so let's look at Chapter 9. Now, Chapter 9 is going to introduce a lot of new things. So don't hesitate to reach out with questions. If you have, and don't feel bad if you have to go back and rewatch a couple parts of the video more than once, all right? So let's jump in here, and I'm going to go with a dark blue for the pen today. All right. Okay, so a little bit of review from last year. All right. We know that from a Lewis structure, we can see the bonding and the lone pairs and all that good stuff. But unfortunately, a Lewis structure does not give us three-dimensional shape, right? And we know that that compounds are three-dimensional things, right? They're physical entities. So a Lewis structure is great, and it's a good starting place to help us determine the shape. So here are some of the common three-dimensional shapes, though, that we might see. And you can see, the trigonal pyramidal shape, right? There's our pyramid, pyramid structure, that kind of thing. There's a T-shaped molecule, which is a new one for us. We're going to see a couple more new ones in a minute. So how do we determine that shape from the Lewis structure, or just in general? Well, electrons repel each other, right? We know from last year that Vesper tells us that the valence shell electron pairs repel each other. Since we assume that they're going to get as far away from each other as possible, this lets us determine what orientation in space they'll occupy, right? Those bonds and those atoms will occupy where they're as far away from each other as possible. Now, just some new terminology for you compared to last year. When we talk about where electrons point, we call those electron domains, all right? In this case, we have 1, 2, 3, 4 electron domains, all right? These are the directions that the electrons are pointing. And when we're talking about valence shell repulsion, we're looking at Vesper. We want to find the arrangement where some number of electron domains are as far away from each other as possible. That is, we want to minimize the repulsions among them. That's what this means. Get them as far away as we can. Now, a lot of times we would take some balloons and tie them together and say, like, okay, this is linear and this is trigonal planar. This would be like tetrahedral. Let's see if I can draw this correctly. Right, so we have like our dash bond and our wedge bond and then our two square bonds, right, straight bonds. What we're actually talking about when we talk about that is the electron domain geometry. So last year we just said, what's the shape? And you said, oh, linear, trigonal, planar, whatever. Now we're going to say, define the electron domain, all right, or define the electron domain geometries. All we're doing is giving it the correct language, all right? If you want to determine this domain geometry, then we need to know the total number of lone pairs, single, doubles, and triple bonds in an atom, all right? 2 electron domains is going to be linear. 3 is probably going to be trigonal planar, right? 4 would be tetrahedral. 5 and 6 are new ones, right? So familiarize yourself with these two shapes. Trigonal bipyramidal, you can see that there is pyramid number 1 on top. Here is pyramid number 2 on the bottom. So there's your bipyramidal. And these 3 lobes are responsible for the trigonal part. All right. Also, we have octahedral, which has a nice, there's 1 face, 2 faces, 3 faces, 4 faces on top. And obviously, when you flip that, that gives you a total of 8 faces all around. Now, when you do molecular geometry, or when you identify those molecular geometries, you often want to start with your Lewis structure and then draw it in 3D in such a way that you can identify it by sight, right? Remember that a wedge bond means it's coming out of the page at you. A dashed bond is going away from the page, and anything that is just a regular old stick bond, right? These things, stick bonds or bar bonds, whatever you want to call them, line bonds, they are flush with the plane of the page, okay? Now, if you look at, we're going to go through and look at each one of these real quick, but linear is probably the easiest one. In linear domain, there's only one molecular geometry, linear, okay? You have, if you have two atoms, you have to be linear, right? But if you only have two electron domains, right, two places for the electrons to go, then you're going to end up with a linear molecule. So a great example of that is CO2, right? It has domain number 1, domain number 2. So we have two electron domains, so you must be linear. Or trigonal planar, all right? Trigonal planar and bent both occupy the 3 electron domain category. So if all of the electron domains are bonding, then you're trigonal planar. If one of them is a lone pair, which would be this right there, then you're going to be in the bent position, all right? So we look at bonding domains compared to non-bonding domains. 3 and 0 compared to 2 and 1. Tetrahedral has 3 molecular geometries, all right? If you have 4 electron domains and everything is bonding, then you are tetrahedral. If you have 4 electron domains and one of them is non-bonding, so a great example of that is ammonia, right? There's our non-bonding region, then we are trigonal pyramidal. And if you have 4 electron domains and you have 2 non-bonding regions, like water, then you are bent, okay? So tetrahedral shape, and like this is important, this shape is the same shape in all of these molecules, right? That tetrahedral shape. Now, when it comes to defining the bond angle, we have to differentiate between non-bonding pairs and bonding pairs. So a non-bonding pair is bigger physically, like in actual reality, is larger than a bonding pair. It takes up more space. So the repulsions are greater. So if I compare the bond angle from tetrahedral, which has no lone pairs, right? No non-bonding pairs. I have 109.5, which is obviously larger. Then if I look at ammonia, which has 1 non-bonding pair, right? It's smaller than 109.5. And over here, I have 2 non-bonding pairs. And so obviously 104.5 is less than 107, right? So non-bonding pairs take up more space than bonding pairs. Now, if you have multiple bonds and you want to look at the bond angles, then you have to think about it in terms of electron density. So double and triple bonds have larger electron domains than single bonds. They have more electrons in them, right? So greater electron density means they're going to exert a greater repulsive force. So the angles become greater, right? Now think about this. This is the driving force making this number right here, the 124.3, larger than the 111. So you're getting more push in this direction, right? Strong force away from that double bond, right? Greater electron density, greater repulsion. Now, there are some elements we talked about in the other video that can break the octet rule. They make more than 4 bonds. This means we can have additional electron domains. You can get 5 or 6, right? If you look back at that slide with the pictures, right, where we talked about why it's called trigonal bipyramidal or octahedral, you can see those electron domains. Now, there are 2 distinct domains that you'll see in trigonal bipyramidal, or 2 distinct positions, rather. You'll be able to talk about the axial positions, which are the atoms above and below the plane of the triangle, and the equatorial position. So here is the equatorial triangle. It is like if we were to draw, let's see if I can, this is going to be tough to draw. If I was to draw a piece of paper, right, then all of this, right, would be in the plane of the paper. It's sitting directly on this piece of paper. But this stuff down here is below, and this here is above. All right, so hopefully you can kind of see that. We can talk about axial atoms and equatorial atoms here. If you have lone pairs in trigonal bipyramidal, they're always going to show up on the equatorial positions. So these guys with the X's, that's where we would see our lone pairs. They won't be on the axial positions, okay? And why, right? We don't just want to say something and not know why. Well, if I put a big lone pair up here, I would expect it to force these bonds down, and now they would be below the plane of the paper. It would no longer have the same geometry. Now, there are 4 molecular geometries in the domain that has 5 electron domains. You have trigonal bipyramidal, you have seesaw, we have T-shaped, and we have linear. All right. Linear is going to look exactly like regular linear, except I've got 3 lone pair non-bonding regions at the equatorial position. The axial position has 2 bonded regions. All right. If we look at T-shaped, again, we have 2 non-bonding regions, again, at the equatorial position, which leaves us with 1, 2, 3 attached atoms, 3 bonding domains. If we look at seesaw, all right, seesaw has 1 non-bonding, again, at the equatorial position. And so I have equatorial, equatorial, which is going to make like a seesaw shape, and then my axial stays the same. If I look at true trigonal bipyramidal, then I have no non-bonding domains, all right? These are great example molecules that you'll probably see me pull from when we are talking about these things. So keep those in mind. Now, the last domain we're going to look at is the octahedral electron domain. It has 6 potential bonding domains, all right? There are 3 geometries here. If you have all 6 bonding domains occupied, then we are octahedral, right? So we have 4 equatorial and 2 axial, right? So 1, 2 axial, we have 1, 2, 3, 4 equatorial. If we have 1 non-bonding domain, right, we see it right there at the axial position, then we have square pyramidal. So there's the pyramid, right? Square pyramidal. Okay, there we can see it. We also have square planar, which literally just looks like an X, and you have the non-bonding regions on the axial, the 2 axial atoms. Now, those geometries are great for smaller molecules, but once we start to get to really big molecules, especially in like organic chemistry, then we stop trying to describe the molecule as a whole, right? Like, and I don't want to like scare you away from chemistry, but you know, you've probably seen benzene before, right? We usually draw it like that. Well, something you should know about benzene is it's not flat, okay? You know, it's got a 3-dimensional shape to it. And when you start, you know, adding other, you know, rings and functional groups and stuff on, like, I mean, you know, here we go. We'll just add a bunch of random stuff. Like I start adding stuff. Okay, I can't give that a shape. That's not going to work. So I can't, you know, rely on the geometry description anymore. So instead, what we start to do is we just look at the geometry about the atoms that we care about. So like in this case, if I'm talking about this oxygen atom right here, or rather carbon atom, sorry, this carbon atom, then I would say the geometry about this carbon atom is tetrahedral, and I can see it right there. If I was to look at, say, this carbon atom, I'd say, well, these are all planar. There's 3 of them. That's trigonal planar, all right? You know, one down here, let me move this out of the way. For this oxygen, all right, it's going to have 2 lone pairs. It's going to be bent, right? So when we get to larger molecules, we can just look at the atoms that we're interested in. Now, polarity comes back into play here, right? So when we're looking at the shape of a molecule, the location of those electrons may indicate that that molecule has some polarity. So kind of a thought process for looking at a 3-dimensional structure and saying, is this polar? Is this a polar molecule? Is there polarity present? So start with this question. Is it covalent or ionic? If it's ionic, it's not polar. Don't worry about it. If it's covalent, next question becomes, are the bonds polar? So we could use our electronegative difference about that or our knowledge about the trend. If the answer is no, if you have a covalent bond and the bonds are nonpolar, you have a nonpolar molecule. If the answer is yes, then we need to look at where the partial charges are and if they coincide. What do we mean by coincide? Well, take carbon dioxide as an example. Those double bonds are polar bonds, they're polar covalent bonds, but the dipole moments start at carbon and push out, okay? So the net positive is centered right here over carbon, and because I have the same balanced negative out here and out there, the balanced negative coincides, right? They're sitting right there over the middle. So even though carbon dioxide has polar covalent bonds, it's a nonpolar molecule because the positive and the negative coincide. If the answer is no, if they don't coincide, then we know the molecule is polar, all right? So that's something that we often look at. And here is a great example of that again, right? It's almost like I knew that was on the next slide. So I have my electric potential map. I can see I can find a lot of electrons here, a lot of electrons there, but the overall dipole moment is zero because they're canceling out, right? They're just centered right there in the middle of the molecule. Now, if you look at something like, we'll say maybe this is water, all right? There are lone pairs up top. That was the worst lone pair ever drawn. There we go. They look like weird ghosts. Right, there are lone pairs that are sticking out. Now my dipole moment is not centered, right? My center of positive charge is between these two things. So it's about right there. My center of negative charge is going to be up top. That should be a negative sign, all right? But when you divide the molecule this way, you can see I've got positive on this side of the molecule. I've got negative on that side of the molecule. They don't coincide. They're not canceling out. Now, valence bond theory tells us that, and we're kind of switching gears a little bit here, because we want to talk about how the electrons actually bond with each other. How do they work together to create a bond? So valence bond theory tells us that if electrons of two atoms get close enough, their orbitals will overlap. And the sharing of space between two electrons, if they have opposite spin, creates creates a covalent bond. Now, we can graph that out and try to determine the actual bond distance, because as the overlap increases, the electrons and the nuclei of two different atoms get closer and closer together, and we have that electrostatic attraction between nuclei and the electrons. But if they get too close, then that nuclei and that nuclei are going to repel each other, right? They're going to push away. And so we look for, we graph the energy, and we look for the lowest point of energy here, where there is a balance between the repelling forces of the two nuclei and the attractive forces between the nuclei and the electrons. That's one of the ways we figure out the distance between, in this case, hydrogen, right? This is the hydrogen distance in H2. Now, Vesper is great and all, but let's kind of look at how that lines up with reality and our understanding of orbitals, right? So we're going to look at H2O. So let's draw H2O. I've got a hydrogen, an oxygen, an H, right? There we go. So we know that this is a bent molecule. We know that though oxygen is got 2s2 and 2p4. So when it gets this electron right here and that electron right there, we would expect that to be in the 2p orbital. And we know the p orbitals, right, are on 90 degrees on the axis, right? You could have, 2p y, or we could have 2px, or we could have 2pz. So we would think, well, why wouldn't it be a 90-degree angle, right? Whichever angle, if it's on the y-axis, right, or if it's on, the z-axis, or if it's on the x-axis, why would it not be 90 degrees? Why would it be 104.45? Well, when they overlap, you get hybrid orbitals. So hydrogen is bringing those electrons in the s orbital. They're going into the p orbitals. And so that's going to make a new kind of orbital, an sp hybrid orbital. And we often call these degenerate orbitals because they're new orbitals, but they have equal energy, but they're not truly s or truly p. Right? If you have two orbitals mixing, you create two orbitals. If you have three orbitals mixing, you're going to create three orbitals. If you had four orbitals mixing, you create four new orbitals. All right. And what we call that is sp hybridization. So if we look at beryllium, right, we can see that you've got paired electrons in full sublevels. Beryllium is going to make electron deficient compounds with two bonds for beryllium because that sp hybridization is going to mix an s orbital and a p orbital. Okay. What does that look like? I'm more visual. Like, this is great. It's a good definition. I'm a visual guy. I want to see it like this. So what do we mean when we say we mix it up and we get two degenerate orbitals that are hybrids? All right. Well, this is an s orbital. It's spherical. Here is a p orbital. It's lobed, right? That's how we would describe the p orbital. When they hybridize, you get this larger lobe, right? So this lobe right here is larger than the original p orbital, and it's a little bit more rounded, right? So it's more rounded. The s orbital together, right? The two hybrids together make this thing, which is bigger than that, right? This is larger than that thing right there. So there's our hybridized orbital. This little thing is called the bonding lobe, and this would be the antibonding or the node. All right, more on that in a little bit. So where do they appear, right? What happens? Well, if you have beryllium and say fluorine, all right, then those s and p orbitals are going to be 180 degrees aligned away from each other. That's because you go back to the electron domains. We only have two here, so it has to be linear. If you go up and you start to look at things with three electron domains, so things like an s and two p orbitals, then we get what's called sp2 hybridization. So we have one s, we have two p orbitals that we're using. And so now we look at it and we say, okay, well, where are they in space? Well, as the s and the p are going to combine, you're going to make a larger lobe, a larger lobe, a larger lobe. There's three of them, so they're trying to get as far away from each other as they can. So we would expect to have some kind of like trigonal planar look, and sure enough, that's what we get. If you look at carbon, carbon has sp3 hybridization. So we have the s orbital, and we have the px, the py, and the pz orbitals together. And so that's going to hybridize to give us four sp3 hybrids. When you put them all together, you get this nice tetrahedral shape. And so that's where we're kind of bringing the electron domains, right, how much bonding can occur, into the shape. Now, sometimes this can lead to hypervalent molecules, and they have more electrons than an octet should hold, right? And the valence bond model would say, well, we got to use the d orbitals for that. And when you actually find this out in nature, that's going to be all of the elements that are in period 3 and below. Now, you can get into some theory that goes with this that says like, this isn't going to work. But we know that the d orbital is involved in some subshell bonding. And so you're going to look at this if you go into further chemistry, but we're not going to get into Coulombic repulsion and spin attraction and that kind of stuff in our class. It's just beyond our scope, all right? But it is out there. You can read about it if you want to. So let's go back to water, right? We started this question with water. We said, why is it not 90 degrees? Why is it 104.5? Well, you've got two bonds and two lone pairs. So this gives me 1, 2, 3, 4 potential places for electron domains. Well, looking back at that chart, if I have 4 electron domains, 2 bonding and 2 non-bonding, then I have a bent molecule, and this matches the sp3 hybridization, which is something that we would expect to see there. Why would I expect to see it? Okay, let's go back. Why would I expect to see that? Makes sense to me. It doesn't make sense to you. Okay, so look, 4 electron domains, 2 are bonding, 2 are non-bonding, but there is that nice tetrahedral shape, okay? This is the sp3 shape right there. There it is, those available places. That's why I would expect to see that. What can we pull out of all this? What's the summary? Number 1, draw the Lewis structure, okay? Vesper tells us what the electron domain geometry is. Is it linear, trigonal, planar, tetrahedral, whatever? Once you know that, then you can figure out how many hybrid orbitals you need to accommodate those electron pairs. This is where we say, okay, I need S, I need P, I need P, I need P. Okay, so it must be sp3. If I only need the S orbital, the P orbital, and the second P orbital, then it's sp2. If I only need S and I only need one P orbital, then it's sp. All right, so that's how I use this. Now, there are more than just single bonds, right? So how does a double or a triple bond work with hybridized orbitals? Well, the simple answer is it can't if you only have hybridized orbitals. But there are other kinds of orbitals that are not hybridized. They have sideways overlap, not end-to-end overlap. So we end up with 2 kinds of bonds that we see in molecules. We have sigma bonds, which are symbolized by sigma, and we have pi bonds. Now, sigma bonds are always head-to-head overlap. You get this like nice cylinder shape, right? And my single bonds are always sigma bonds, okay? Pi bonds are side-to-side overlap. So they're not running through the internuclear axis, right? So here is the internuclear axis. It's an imaginary line running between the 2 nuclei. And instead of, lining up head to head, they are above and below or, side to side. So this is often how we draw it for a pi bond. But this is like really what we're looking at. So if this is my internuclear axis, there's my nuclei. Right? I have p orbitals that are above and below. This is where I'm going to get side-to-side interaction. So if I want a double bond, what's that going to look like? Well, here is an sp2 hybridized orbital. I'm using 2 of the p orbitals and 1 of the s orbitals, and I've got this nice overlap. This is how I'm going to end up with a double bond. So there is my single bond, all right? And I'm going to get a double bond right there. All right. Now, something to keep in mind, you cannot put a bond in both of these. One of these is we'll call it the bonding. One will be the anti-bonding. All right. Now, if I look over, so I can get a bond here and then the single bond. So this would be a double bond. If I look over here to get a triple bond, right? My single bond's in the middle, and I can see it there. That head-to-head overlap, it's in purple. So there's my single bond. And in this top one and in this side one, there's my triple bond. 1, 2, 3. Okay. Multiple bonds have to have 1 sigma bond to start, and then the overlap comes from the pi bond. So I can see this back lobe and the front lobe are overlapping. The top lobe and the bottom lobe are overlapping. Well, if we're going to talk about these bonds and we're going to talk about where these electrons are, then we need to be able to define those electrons as localized or delocalized. So bonding electrons that are specifically shared between 2 atoms, they're not resonating, they're not moving around or anything like that, are called localized electrons. Great example would be oxygen bonded to oxygen. I said this in the other video, right? Those bonds right there, those electrons in those bonds are localized electrons. Now, a lot of molecules, you can't do that. So if you look at something like benzene, right, benzene has delocalized electrons because the resonance structure is these are moving, all right, and they're moving constantly, okay? So the resonance structure means that at all times, these carbon atoms don't have like this carbon atom, right? So we'll draw it out. So if you were to look at these two carbons right here, you would say these have a double bond, these have a single bond, these two have a double bond, these two have a single bond, these two right here have a double bond, and these two have a single bond. And then if you do the same thing over here, now it would change. So we'll call this C1, C2, C3, C4, C5, and C6. So 1, 2, 3, 4, 5, 6. So right now we'd say double there, single there, double, single, double, single. And if we were describing who has what bond, we would say, well, in this picture, 1 and 2, carbon 1 and 2 have a double bond. But in this picture, carbon 1 and 2 have a single bond. We would be wrong. They're resonating. So what they actually have is a 1.5 bond. All of them have a 1.5 bond all the way around. Now, I know that you're thinking, how can you have a half bond? That doesn't make any sense. Well, I know. But when we're trying to describe subatomic, submicroscopic behavior, remember, some of the rules in our macroscopic world might not be great examples. So when we think of a bond, right, we think of, this. That's not what we're talking about here. The bond is more, I'm going to use the word ethereal than that. It's the sharing of electrons. It's not, the throwing of a tow rope. All right. So in a 1.5 bond, we have some characteristics of single bonds and some characteristics of double bonds, right? That's what we're looking at there. Now, this brings us to molecular orbital theory. And I really like molecular orbital theory because it incorporates the fact that there are wave properties and that electrons have that can be used to describe the energy of the electrons in a molecule. Now, MO theory has a lot of characteristics just like atomic orbital theory does. Like, you can only put 2 electrons per orbital seat. All right. So just like when we said, in year 1 chemistry, like here's 1s, you can put 2 orbitals in that seat or 2 electrons in that seat. That's it. Okay, that's still true. If I have like 2p, right? That's it. I can put 2 in a seat. I can't all of a sudden do 3. Like, that won't work. All right. The electrons in the same orbital have to have the opposite spin. So we're still abiding by Pauli's exclusionary principle. There is a definite energy associated with each orbital. So that's still good, right? The further away you are from the nucleus, the more energy you have. But now we can visualize this electron density using a diagram. Now, they are different from atomic orbitals in that they can talk about an entire molecule, not just an atom. So, when we're doing like 1s2, this is, helium. We're just talking about one atom. With molecular orbital theory, we can talk about the entire compound or, a whole molecule. If you have 2 overlapping atomic orbitals, then you make 2 molecular orbitals that are being formed. One's called the bonding orbital, one's called the anti-bonding orbital. In bonding orbitals, we're taking into effect the wave characteristics. So you have constructive combinations of the wave-like behavior. In anti-bonding orbitals, we're saying that the destructive behaviors of waves cancel out that atomic orbital. Or that molecular orbital. Nothing's going to bond there. And that brings us something called a nodal plane or a node. And it's basically where you have 0 electron density. All right, well, what do we mean by that? Well, if I have 2 s orbitals overlapping, right, I'm making a sigma bond. Then I've got my bonding orbital and I have my anti-bonding orbitals. So remember that electrons can move as waves. So if these 2 waves come together, if they're equal and opposite, then the resultant wave would be nothing, right? It'd be a flat line. But on the other hand, since these 2 waves are coming together, they're going to build a bigger wave, right? They're going to constructively come together. So this one is the bonding orbital. It's constructive, constructive interference where the wave gets bigger. This one is going to be anti-bonding. It's where, they come in and they cancel out. All right. We signify the anti-bonding orbital with the asterisk, and we just don't have one for the bonding orbital. We know that electrons like to go in lower energy orbitals first. The bonding orbitals are lower in energy on this graph than the anti-bonding orbitals. All right, a lot of new stuff. How can we use it? Well, let me ask you a question. Is it possible to prove that you can't make diatomic helium? We know helium's a noble gas. We know, oh yeah, of course not. Can you prove it? Yes. So this is the molecular orbital diagram for hydrogen. We're going to start with hydrogen, then we're going to answer the question about helium. So let's first start with, can H2 form? All right. Well, the hydrogen atom has a 1s electron. So here's hydrogen atom number 1. Here's hydrogen atom number 2. Actually, we'll call them A and we'll call them B because I don't want you to think that's H2. Well, in H2, the 2 electrons go into the lower energy molecular orbital. So this electron is going right there. This electron is going right there. And with this, once I have this thing, all right, my molecular orbital diagram, that's what this is called, I can calculate bond order. So bond order is really easy. It's 1/2 times the number of electrons in the bonding orbital minus the number of electrons in the anti-bonding orbitals. So here I have 1/2 times 2 minus 0 because there's nothing there, right? I have to fill up this lower energy first. I can't put them in this antibody. So I have 1/2 of 2 minus 0. So I have 1/2 of 2. So that is a bond order of 1. That means I have a single bond. So yes, that checks out. Now look at helium. So helium has 1s2, right? So there's 1s1, there's 1s2. So if I want to put 2 helium atoms together, all right, well, that one goes there, that one goes there. Now this one goes here, that one goes there, right? I have to fill them up. They're overlapping. Well, let's do our bond order. 1/2, 2 at the bottom, minus 2 at the top. Well, 1/2 of 0 is 0. I have a 0 bond order. It means there's no bonds. It can't exist. And this is really, really a useful thing, right? If we're trying to figure out and prove, like, hey, can we make this compound? Now, you can get your S&P orbitals to interact and form these bonding and antibonding orbitals. This is what you're doing every time, all right? So I have atomic orbital. It's going to create antibonding MO, molecular orbital, and bonding MO. Remember, bonding is always lower on the energy scale in a molecular orbital diagram than antibonding is. If you get face-to-face or end-over-end overlap, you're going to make sigma bonds. If you get sideways overlap, you're going to make pi bonds, all right? Let's see a molecular orbital for, let's see, which one did we put in here? Oh, I didn't put one in here yet. So let's just, we can use this kind of as a general form. Sorry, I was getting ahead of myself there. Let's say we wanted to do, I'm trying to think of an easy one. That's 2p. Let's do N2. So let's see if we can get N2 to work. So we know that nitrogen is 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. So we know we have 1s2, or sorry, 2s2. Sorry, we only look at the valence energy levels. So 2. And we have 1, 2, 3. And we're doing a diatomic, so it's the same on both sides. All right. So we go 1, 2, 3, 4. That accounts for the bottoms. 1, 2. So we have 6 electrons. So 1, 2, 3, 4, 5, 6. So we have nothing up there. So what's our bond order for N2? We say 1/2. We have 2 bonding, 4, 6, 8, minus 2 in the anti-bonding category. So we have 1/2 of 6. So we have 3. So we have a bond order of 3. Well, let's draw N2. We know that if we draw this out and we try to do a Lewis diagram, we have 5 electrons for each. We have a total of 10 electrons. Unfortunately, here we've used 2, 4, 6, 8, 10 to a 14. So we would have to share electrons. This is the correct drawing. Look at there. we have a triple bond, and our bond order is 3. See how that works? Nice, easy stuff, right? Super simple. Welcome to AP Chemistry. Now, when we look at S&P interactions, right, non-identical bonding like S and S or P and P, then sometimes that changes the energy levels as far as the hybrid overlap. So like the sigma 2p would go above the pi 2p. I'm not going to really have you guys look into that with any great depth, but just be aware it can move the energy around when you have S&P orbital interactions. You will see one of those in a minute. Now, just so you see it. So let's look at the MO diagrams for some diatomic molecules in the second period, like B2, C2, right? N2, we can see they've left out the atomic orbitals. They're just showing you the molecular orbitals that were in the middle of that diagram. And down here at the bottom, we can see what I think is probably the most important right now is the bond order. So if I want to draw C2, I have a bond order of 2. I would expect it looks something like that. Well, let's see. We've got 2, 4, 6 in the bonding, minus 2. So that's 1/2 of 4, bond order of 2, double bond, 2, 4, 6, 8, 10, 12 electrons, 2, 4, 6, 8. Wait a minute, what did I do there? That would be what I would draw, sorry, even though that doesn't perfectly align with my my knowledge of Lewis diagram, sorry. So would we expect to find that? What about N2, right? We just did N2. We have 10 total bonding electrons. We know it's going to look like this. We get our 3 right there. All right. Now, something else that's interesting that comes from the molecular orbital diagrams is paramagnetic and diamagnetic properties. Now, diamagnetism is when all of the electrons in your orbitals are spin paired. They are weakly repelled by a magnetic field. Paramagnetism is when you have one or more unpaired electrons in an orbital. So what if we asked a question, we said like, hey, is oxygen paramagnetic? Well, when we look at oxygen, we can see that we have some unpaired electrons, right? They don't have that down spin. And so we would say, oh yeah, it's paramagnetic, right? It has one or more unpaired electrons. Now, this is an advantage over a Lewis structure because a Lewis structure would not predict oxygen is paramagnetic, but the molecular orbital diagram shows that it is, okay? And so in paramagnetism, you are attracted to the magnetic field, okay? So that's cool stuff. Now, the last thing we're going to look at, last slide, promise, is one of the more interesting compounds. We're going to look at NO. And we know from the other slide, the other video on this unit that we did, the NO is a radical species, right? It has an odd number of electrons. It has 11. So N gives us 5 and O gives us 6. That's a total of 11 electrons. If we layer that into a molecular orbital diagram, then the first thing you might notice is that like this 2p and that 2p are not even. That's because there are different levels of energy based on how electronegative you are. So more electronegative atoms, which in this case O is more electronegative than N, should be lower on this energy scale for degenerate orbitals, right? The same orbital, 2p. Now the other thing that's cool is if you look at the bond order, all right? So we've already filled in the arrows, right? And we see we got this one unpaired electron up here, right? This is an antibonding node. There's our other antibonding node. So when we do bond order, we have 1/2 of 2, 4, 6, 8 minus 2, 3. So that's 1/2 of 5. So our bond order is 2.5. All right. Well, can we draw a 0.5 bond? No. If I want to draw this, it's going to look like that. But there is probably some resonance, Okay, so we could have this, right? There would be a resonance form. Okay, and what this 2.5 bond order means is that this bond has characteristics of a double and a triple bond. That's kind of how we interpret that. Okay, so now that's a lot of new stuff. If you have questions, shoot me an email, let me know, and I'll be glad to give you a hand. All right, so see you in the next one.